The RTL was successfully developed for this ASIC/FPGA system. After functional verification, we also synthesize the unit into a gate-level netlist. Then timing verification was performed to verify that the system-on-chip multi-core system meets timing requirements. Once the design meets timing goals, the netlist is given to the physical design, which places and routes the design, and then finally the chip is built and tested. The high-level system design process applied in this design was as follows. First, I identified the system requirements, followed by writing the preliminary specifications and parameters, thus developing a high level of algorithmic models in both C and C++ and also in VHDL. After that, I refined and tested the algorithms and determined the hardware and software partitioning at a system high level. Then I defined the interfaces and the software specifications were written and to develop the prototype of the software. The hardware-software co-simulation was also performed, and the hardware specification was developed with behavioral models for the system. The partition was developed with reference to macros. Several macros were developed, and the preliminary specification was written for those specific macros. At the top level HDL, I successfully determined the configuration and generated the top level HDL design. In parallel, I completed and generated synthesis scripts, synthesized with reference to the library, provided scan insertion, ATPG fault simulation, and also perform the final timing and power analysis. Also in parallel, provided functional verification with a reference simulator, developed and ran multiple test configurations, and measure test coverage. For those sections of the design that are full custom, we have the choice between manual porting and automated porting. Under certain circumstances, automatic porting tools such as Gigantic, Dream can be effective. These tools operate at the polygon level, automatically mapping transistors and interconnect from one set of design rules to another, and shrinking the design as much as possible. For large macros such as multi-core embedded systems, where simulation speed in the system environment may be an issue, it can be useful to include cycle-based simulation and/or emulation models. In general, RTL that complies with the coding guidelines will work with cycle-based simulation and emulation. However, test benches and bus functional models, unless coded to the same RTL guidelines, are important and effective for large macros. The product files, in addition to the RTL in Verilog and VHDL, we must include the synthesis and installation scripts. We include the reference library so that we can synthesize the design and verify that the installation was completed successfully. In addition, providing the reference library, scripts, and verification environment allows us to create this true environment. Porting the hard macros. For hard IP that was completely synthesized, the porting strategy is quite straightforward. We just resynthesize, targeting the new technology library, and repeat the physical design and timing model generation. In this framework, I will present the topics of placement and routing within an ASIC design methodology. However, before we start this segment, we need to talk about physical design methodology in general. So many interdependencies exist among placement, clock and scan optimization, wiring, as well as hierarchical design planning. The general design flow is as follows. First, identify connections to be optimized after placement so that they will not influence placement at all. These include the scan and clock interconnection latches. 2. Generate constraints for placement on the basis of a timing analysis done using idealized clock arrival times at latches and estimates of wire load and RC delay before physical design. 3. Perform an initial placement to determine an improved basis for constraint generation and optionally to fix the placement of large objects. 4. Generate new constraints for placement on the basis of a timing analysis done using the wire load and RC delay values derived from the initial placement. Perform placement. 6. Optimize the clock trees and scan connections. Then make logic changes, including changes to circuit power levels, to fix timing problems. Then 8. Legalize placement. And then generate the new timing constraints for wiring on the basis of a timing analysis done using the actual clock tree and wire load and RC delay values derived from the final placement. And then finally, perform routing. So, placement is often run before the logic has been finalized to obtain an early indication of the timing and wireability. At this point, the feedback may be used to influence the logic changes. This may also be the time at which the locations of large objects are determined. The placement program may run more quickly by not considering such details as legality, and there are maybe less emphasis in achieving the best possible results. The results of this placement may be used as input to the tool which generates capacitance constraints used to derive subsequent placements. Here I perform placement and routing using a sophisticated tool by Cadence known as Innovus. Legality incorporates such constraints as the circuits not overlapping one another and remaining within the bounds of their placement area, being placed in valid orientations and in rows specified in the chip image, satisfying other restrictions supplied by either the user or the technology. Once the logic has stabilized, more emphasis is placed on achieving a high quality and legal placement. Some placement tools do ignore at least some aspects of legality during the optimization phase. Both clock optimization and power optimization. This overlap can simply be removed through a brute force technique, or overlap removal can be performed with some of the placement optimization. It is important to ensure that the quality of the placement is maintained, such as clock skew, timing, and wireability. For instance, the smallest clock skews is achieved by preventing the circuits in timing critical clock trees from moving during overlap removal. The basic algorithms used in our placement programs are simulating annealing and quadratic placement with iterative improvements. These are by no means new techniques, but the programs have been continually enhanced to give better results in general and to support the new specific technology-driven requirements. The simulated annealing placement program now has the capability of performing low temperature simulating annealing, LTSA. So LTSA determines the temperature at which an existing placement is in equilibrium and starts cooling from the temperature, thus effecting local improvements to a placement without disrupting the global placement characteristics. Both simulated annealing and quadratic placement accept many controls. They include pre-placement, for-planning, specification of circuits to be placed in adjacent locations, net capacitance, and source to sink resistant constraints, and weight for the various components of the scoring function, including net length, congestion, and population balancing. The routing program receives guidance from the clock optimization program for nets in clock and other timing critical trees in the form of floor plan routes. The routing program breaks each of these multi-pin nets into a group of point-to-point subnets. Each of these subnets is then routed to match the delay selected by the clock optimization program as closely as possible to achieve the desired electrical and noise characteristics. You can specify the wire width and specify to be used for each net. Clock nets are often given a wider width and spacing to reduce their resistance, capacitance, and noise. High clock speeds and long, narrow wires can result in a reliability problem known as electromigration. Over time, the movement of electrons can move the metal atoms and result in a break-in the wire. So we want to fine-tune the wires for some nets, such as clocks, and keep these wires fixed through multiple passes of engineering changes. At the end of routing, all new wire segments are assigned to a user-specified group. The routing program makes sure that nets routed in one iteration do not prevent the remaining nets from being completed. This allows me to have the program route just the clock nets in the first iteration. Once it has been verified that these routes meet the clock skew objectives, the wires for these nets can be fixed during the remaining iterations. A set of timing critical nets can be routed in the second iteration after analysis has verified that these nets meet the timing objectives. The remaining nets can be routed in the third iteration without changing the wires for the clock and timing critical nets. This methodology allows tight clock skew and timing objectives to be met. It also allows timing problems requiring logic or placement changes to be identified quickly before running a relatively long routine iteration on the majority of the nets. In this segment, I have illustrated the place and route of an artificial intelligence arithmetic logic unit, ALU, for a design implemented in ASIC 7nm system-on-chip technology.